Okay, so now we're going to move on to a topic which I think ironically is probably the most difficult aspect of the Southern Ocean to actually try to resolve with observations, thinking about meridional overturning. And we're very lucky to have here from Australia Andy Hogg. He's an associate professor at Australian National University. He's also the leader of the geophysical fluid dynamics group there. And Andy has worked on a broad range of different physical properties in the ocean. He's interested in very large scales and long time scales, so looking at interglacial changes in the climate, and also sort of going down to very, very small scale mixing, mesoscale, submesoscale dynamics, and in some cases actually looking at both of those together. But I think where Andy has really provided a lot of insight to the Southern Ocean community is working with various, really a hierarchy of different models to look at Southern Ocean overturning. And I think what's really nice about his paper is that he has a really good insight into what is the really just the right amount of complexity you need to sort of resolve different physical processes. And so I think probably that's what he'll talk about in the next talk. So thank you very much, Andy.
Okay, thank you, Andy. Thanks to both you and Nicola for organising this workshop and assembling such a great cast of speakers for the week. So my instructions were slightly different from Mike's, actually. He didn't ask me to be controversial, but he did. Andy did ask me to make this accessible to both the biogeochemists and the members of the public who have turned up today, which means that if you've spent your life working on residual mean theory, you've probably seen a lot of this before. So apologies for that. But I think one of the goals we have with this talk is to try and the ensuing discussion afterwards is to try and put us all on a similar footing for the remainder of the week and to give a broad overview of what we do and don't know about the Southern Ocean overturning. So this is a figure you're probably going to see a little bit of this week. This is finally at last published in a Physics Today article that Adele Morrison wrote this year. And the reason I'm showing it is to get across an idea of the complexity of the Southern Ocean and the main current systems that are there. So the Southern Ocean is a complex place. If you've grown up trying to understand, for example, northern high latitudes, you probably find the Southern Ocean quite counterintuitive. And there's a few reasons for that. The big difference, of course, between the Southern Ocean and the rest of the world is the fact that through Drake Passage you can get a zonally unbounded flow, which leads to a very different dynamical regime. So there's also very strong westerly winds in the southern hemisphere, which is at least partially responsible for driving the Antarctic circumpolar current around Antarctica, but of relevance to us today also drives the northward Ekman transport in the surface layers all the way around Antarctica and helps to drive this upper cell of the overturning circulation, which I've drawn here. There's also a very complex pattern of buoyancy loss and buoyancy gain that is only partially captured by the observations, in my view. In particular, the buoyancy loss close to the Antarctic coast drives the densest water in the global ocean down to great depth and forms Antarctic bottom water there. And this is what contributes to this lower cell of the overturning circulation here. So I'm going to frame this talk in terms of the upper and lower overturning cells independently. And a lot of the views I will show you will be of a transect across the Southern Ocean. Most of them will be considering the Southern Ocean as a zonally averaged quantity. We're going to start with, I guess, a schematic of how the Southern Ocean might connect with the rest of the globe. So this shows the upper cell connecting, at least in a globally zonally average sense, to the sinking of dense water in the northern high latitudes and being upwelled along isopycnals to this region here. And it also shows the lower cell, which spreads throughout the abyss of most of the global ocean, if not all, and also recirculates along isopycnals up into the Southern Ocean. For the biogeochemists, of course, one of the main features of interest is this excavation of very deep, old, carbon-rich water up to the surface. And I'm going to talk a little bit about how that's done dynamically. But the main thing I want to do today, as well as give you an insight to the dynamics, is to try and frame how we think these two cells might respond to changes in the surface forcing, particularly in the Southern Ocean. Okay, so that'll be the focus. As I said, and as you can see from the menu on the right, I'm going to start with the upper cell, and I'm going to give you a little bit of an overview of the theory, as well as look into what observations and models can tell us. The most interesting thing, I think, is going to be the complications, or as Andy would say, the outstanding questions, which I think we're going to talk about quite a bit during the week. Okay, so let's start with the real basics. And as I mentioned, this is a transect across the Southern Ocean. We've got the vertical axis here. This is latitude in this on the x-axis. And these orange lines are going to be isopycnals, or density surfaces. And if you imagine you start with isopycnals that are flat, and then you apply a wind stress coming out of the page towards you, then that drives, the first thing that will do is drive an Ekman transport to the north in the surface layers, which somewhere in the Southern Ocean must be balanced by a return flow. If you have a zonally unbounded channel, then that return flow turns out to most likely occur at the bottom. And this is what this circulation cell is what you would think of as the mean, or the Eulerian overturning cell in the Southern Ocean. And what that effectively does is it begins to tilt these isopycnals upwards towards the south, and would continue to do so indefinitely unless there is a process pushing these isopycnals back down. The process that pushes these isopycnals back down is eddies, which extract available potential energy from the flow and act to relax isopycnals. And so the primary balance, particularly in the upper cell in the Southern Ocean, is between these eddies and between the wind stress. And that's framed more formally in this residual mean theory idea, which many of you will have seen much about. And in residual mean theory, what you have is you have this wind stress acting on the surface, and you define a mean overturning stream function, which is just shown schematically here in this diagram from John Marshall and Timo Radko's paper. And that Eulerian or mean overturning cell is always acting to tilt isopycnals upwards in this sense. So this theory, residual mean theory, then allows you to quantify an eddy overturning, which generally acts to oppose this mean overturning here. And the sum of these two gives you the residual overturning. And I kind of don't like the term residual overturning, because I feel that the residual overturning is actually the overturning. It's the overturning that particles follow. The mean overturning is a fictitious abstract concept. It's not, it doesn't describe particle paths. It's not where traces would be advected if there were traces in this ocean. So, and likewise, the eddy overturning is not a real thing. It is an abstract concept that allows us to divide this very small residual flow, or smallish residual flow, into two larger opposing circulation cells. But it does allow us to capture a little bit of the complexity, and the reason is because we can understand what this mean component will do very easily. For example, if you increase the wind stress, we know exactly how much this mean component will increase by. Okay? And what that means is that if this term increases, then either this term has to increase in the opposite direction to counter it, that's the eddy term, or the residual overturning will increase. And this leads us to a topic which is of interest at the moment, which I've labelled here eddy compensation. And eddy compensation describes a state where all increases in the mean overturning due to changes in wind are exactly balanced by the eddy overturning in the opposite direction. And if that happens, then an increase in wind will not change the residual circulation. So it won't change tracer transport or anything, okay? So that's what I'm defining as eddy compensation. It's not to be confused with eddy saturation. Eddy saturation is a term you may have heard. It's not relevant to the overturning circulation, and it refers to the insensitivity of the ACC, or the Antarctic Circumpolar Current, to wind stress forcing. I'm not going to talk about this at all today, really, essentially because once I start on that, I'll never stop, but also because it's nothing to do with the overturning. So we're going to have a look at this eddy compensation a little bit more. I have a slightly alternative way of looking at the eddy compensation problem, and I want to do that by showing you this simple model. And I say simple because there's only a few terms in the equation, but to get to this stage requires a little bit of mathematical work. But I'm going to use this to try and demonstrate a point, so I'm not going to be particularly rigorous about it, and I'm not going to derive it for you. But this is a nice little model that we can use to explore MOC dynamics. And what we assume is that we can divide the ocean up into a number of isopycnal layers, okay? And these isopycnal layers might be thin or they might be thick. And I'm assuming here that, let's say we can define an isopycnal which divides the northward flowing waters closer to the surface from the southward flowing return flow, which occurs at depth. And if we can do that, then we can write this equation, and we can write dynamical equations and average zonally and average across our layers and put it in a framework which is simpler to deal with. The equation I use, believe it or not, even though we're talking about the meridional overturning, is the zonal momentum equation. So that's the momentum equation along the ACC. And you'll see why I do that in a moment. So here, u is the velocity in the direction of the ACC, so coming out of the page towards you. So if I average over the layer thickness, h, then I get a transport in that layer, which is the ACC transport in that direction. And then if I make enough assumptions and I ignore lateral momentum transfer and a few other things, I can write an approximate equation for the rate of change of this layer-wise transport, which is a function of three terms, which I'm going to explain to you briefly. Okay, so this first term here is what we call a Coriolis term, and what it is if there's southward transport in a layer, then that southward transport is exerting a force on the eastward flow, and so that's where the meridional transport comes into the zonal momentum equation. Okay. This term here is much more complicated. It's a form stress term, and when I've written the equation in a slightly different form down here, I've written this as the difference between form stress on the top and the bottom of a layer. And what form stress is, literally, or maybe not literally, but to a good approximation, is that if you take a density surface between two layers, if that density surface is more wrinkled, then you get better momentum transport between the two layers. It's not a viscous momentum transport, it's an inviscid momentum transport, which transports the zonal momentum from this layer to that layer, and then from this layer to the layer below. Okay? So that turns out to be an important term in this balance. And of course, the last one is tau. That's just wind stress, and well, that's just wind stress. So that's quite an easy term. So let's think about this for a moment. And if we think about our southward flowing waters here, and just this second layer here, then because in this part, this layer doesn't outcrop at the surface, so it doesn't feel any wind stress in this location. And what that means is that if we're in equilibrium, so we can get rid of this time-dependent term, and this wind stress term is 0, then the Coriolis term, which is the southward transport, is just balanced by the difference in form stress on either side. Okay? Now remember, form stress is proportional to these wrinkles on the isopycnal, so it's essentially an eddy term. Transient eddies, standing eddies, the works. And at these latitudes, the Coriolis term is most likely also a residual eddy term. And what that means is that we've got two eddy terms balancing each other. And that's why eddies are so important to the overturning. If you take this upper layer here, where we do have a wind stress, and we also have a net northward transport, then what you see is that net northward transport at equilibrium is the balance between the difference of form stress at the surface, wind stress at the surface and form stress at the bottom of the layer. Okay. Now in this case, it's only the bottom one which is an eddy term, and also the Coriolis will have part of an eddy term. So you can imagine that if the eddy terms, if you change the wind in such a way that eddies increase, then this term will be affected by a large degree, and this will also be affected. And in my view, you could have a situation where you have partial opposition to this increasing this term, but also an increase in this one here, so that eddies help to drive the southward flow while also helping to resist the northward flow in the layer above. But these two layers have to connect. Okay. So so that's the reason why we might expect some eddy compensation in these in this flow situation, and I'll talk a little bit more about that when I get to the models. But first I want to talk about observations, and observations was really Mike's domain, so I just wanted to highlight this one, and Mike actually mentioned it in his talk. One of the problems we have in using observations to constrain our own understanding of the overturning is there's no direct measurements of the overturning. Okay? And there's also no very good measurements of the buoyancy forcing at the surface of the Southern Ocean. Really the main things we can measure are wind and the eddy kinetic energy, which we can measure from satellite. And for some time there's been some debates about whether the eddy kinetic energy would increase as wind stress increases or not. And models tell you that they will, but until recently we haven't been able to diagnose that signature in the observations. And the point is that now that we can see a coherent long-term trend, particularly in the Indian and Pacific Oceans, that eddy kinetic energy is increased as the wind stress is increased. So that means that eddy compensation is at least possible, but of course we can't observe the overturning at the same time. So to understand whether eddy compensation will occur, we have to look to models. This is kind of a complex diagram. It's just one of a cast of 10 or 20 papers that looks at this problem, and I picked this one because it was one of the earliest papers to look at eddy compensation in a global coupled model. There are many idealized studies, many global ocean-only models. And what you're seeing here is the overturning circulation, and it looks a bit funny because it's in density space. So density is on the vertical axis here. But the point is that what we're interested in is the size of this red cell here, and we're seeing the residual circulation on the top, the mean in the middle, and the eddy term on the bottom. And you can see this is what we mean about the eddy term opposing the mean and resulting in that residual up the top. So when we change the winds, this one on the right shows you a big increase in winds. And what you see is that as you change the winds, the mean overturning goes up. If you squint, you can also see that the eddy overturning also goes up, so that the residual doesn't go up by quite as much as the mean, and that's what we expect if there's partial eddy compensation. But the residual does go up, and that's an effect we see in all models. Okay, so we don't have exact eddy compensation, and we show this in this diagram here. So this is a plot which some of you may have seen before, and I've kind of compiled it from a few different plots. But the point is, it's plotting the eddy overturning as a function of wind stress. So if there was no eddy compensation, then you would follow this solid purple line, because eddies because the eddy overturning would not increase at all with wind stress. On the other hand, this dashed line here is the estimate of where we would be if we had full eddy compensation. And scaling theory tells us this shaded region should capture most model regimes, okay, which is definitely a partial eddy compensation. And you can see that by and large most models fall into that shaded region. A couple of exceptions are at coarser resolution, so in particular this CM 2.1 coupled model from Farnetti et al. Was below the eddy compensation line, and for many coarse resolution models the eddy parameterizations miss out on this eddy compensation effect, although there are some where a more rigorous application of the Gent-McWilliams scheme, such as Gent and Danabasoglu, do see an appropriate amount of eddy compensation. Okay, so that's all I wanted to say on what we know. Now I'm going to talk a little bit about what we don't know. I think one of the biggest complications in this picture is that of surface buoyancy forcing. This shouldn't be a surprise. We've known since at least 15 years ago, Kevin Spear's diabatic Deacon cell paper, that buoyancy gain, which you can see up here, is an important part of the upper cell. And the reason is, in layman's language, if you want to push water northwards across these isopycnals by Ekman transport, then you have to give it buoyancy at the same time. Otherwise it can't be transformed across this isopycnal. Okay? So buoyancy gain in the ACC latitudes is an essential part of the circulation. And to some extent, you can diagnose the overturning from knowledge of these buoyancy fluxes and interior mixing, water mass transformation in the interior, once you have a good picture of what it is. What's more, when you run a model, you find that you can modify the residual overturning by changing the buoyancy flux. So this is one from Adele Morrison's work a few years ago, where you increase the buoyancy forcing on this axis. That results in, almost regardless of the resolution, there's slight differences between the two, which I can explain if you're interested. You get an increase in the overturning maxima at 30 degrees south as a function of buoyancy forcing. Okay? So if you want to increase the upper cell, there's two ways to do it. You can increase the wind, or you can alter the buoyancy forcing. An equivalent way of saying this is the way it's framed by Ryan Abernathy, where he says that the overturning response to wind change depends on the surface buoyancy boundary condition. Okay? So these are really saying the same thing, although we haven't really quantified how it works, and we don't have a good picture of what the actual buoyancy fluxes are. It sounds silly, but another complication is what is an eddy. When I talk about eddies, most of you probably think about vortices spinning around in the Southern Ocean, as in the Hallberg and Janudesican picture that Andy showed in his introduction. But it turns out that meandering jets and also stationary meanders, not only transient meanders, but stationary meanders also turn out to be important. And there is a component of the overturning that can be explained by the contribution of standing eddies. So that's just jets in the meandering jets in the lee of topography, even if there's not a transient component to it. They also help to modify the location of heat transport and the response of the momentum transport to wind. And remember, the momentum is intrinsically linked to the overturning via the film stress terms that I showed you earlier in that theory. And finally, the ACC is a three-dimensional flow. And this is just one example from one of Andy's papers showing the variation of EKE in the Indian Ocean, I think. And the point is here that if eddies are important to the overturning, and eddies are so spatially varying, then is the overturning spatially varying? And this is an important point, because if carbon varies at all along the path of the ACC, then a zonally averaged overturning is not a good description of tracer transport. So, for example, if you increase the upwelling in the Pacific Ocean, where the deep water may have more carbon, then that will be reflected in the same way in the zonally averaged overturning as if you increase it in the Atlantic. But they have very different effects on the BGC. So we need to think a lot more about three-dimensionality, and people are already starting to. Okay, so that's it for the upper cell. Now we're going to switch gears and spend a little bit of time talking about the lower cell. I'm not going to spend as much time on this, partly because I'm running out of time and partly because we know less about it. I'm going to show you another one of these schematics, and I've chosen this one for this occasion because this has all the detail of what's going on at the Antarctic coast, where you have dense water formation due to processes such as katabatic winds, which aren't in most climate models, forming polynyas, which aren't resolved by most climate models, and leads in the sea ice, creating very high salinity shelf waters, which are done poorly in most global climate models, which then feeds the lower cell, as you can see here. On its way, so once you've produced this dense high salinity shelf water and it cascades off the edge of the shelf, and it does so in a way that's not a nice slug of a current that you see here. It's actually little tendrils that are probably time dependent, guided by topography, entraining fluid above it all the way down, as you can see from these arrows, and reaching the bottom. And none of those things are very well done by climate models either. So it's no surprise that models do an appalling job of Antarctic bottom water formation, particularly the CMIP class of models. Once it reaches the abyss, then this Antarctic bottom water, which is the densest in the main part of the global ocean, has to somehow return to the surface. And it does so via water mass transformations and potentially via a process similar to the residual overturning upwelling along isopycnals. So that's our basic picture of the lower cell. And in thinking about how the lower cell might change as we change climate states, we have to ask the question, what actually sets the strength of the lower cell? And to be honest, I'm not sure we can answer that question very well. There's a few candidate mechanisms. I'm not sure that there's a consensus. A favourite of mine is that really what's driving this lower cell is the production of available potential energy by buoyancy fluxes close to the Antarctic coast. That's what provides the energy for this circulation. And then it has to go around this loop. And around this loop, that water must undergo water mass transformations. And it can do that in several ways. It can do it by entrainment on the way down, entraining water from the ambient, or it can do it by interior mixing once it reaches the bottom, once it reaches the abyss. And lateral eddy fluxes may also be important in returning it to the surface. So Hughes and Griffiths pointed out about a decade ago that the more you entrain Antarctic bottom water on the way down, the less interior mixing is needed to balance this system. And one of the problems here is you can always find a model, you can run a model, you can change one of these aspects, and you will get a change in the Antarctic bottom water cell, the Antarctic bottom water formation rate, or the volume of this magnitude of this cell. And that leads me to conclude that perhaps all of the above are contributing to the strength of the lower cell, and that these different forcing terms actually communicate via the ocean stratification rather than any individual one of them governing this circulation. Okay? I think there's a long way to run on that, and I'd love to be able to turn to observations to help us out here. But as Mike alluded to, observations of the deep Southern Ocean are particularly sparse. There is, however, some signatures which are robust in the deep waters. In particular, hydrographic observations tell us that over the last few decades, Antarctic bottom water has been both warming, as you can see in this Perkey and Johnson paper, where isotherms are migrating downwards over the course of between two observations. And this is from one of Steve Rintoul's paper, and this shows the profiles in temperature salinity space. And what you can see is these profiles are shifting upwards and to the left, which means they're both warming and freshening. And so that raises the question as to what is governing this this warming and freshening. And I think without a proper understanding of all the details of the lower cell, we can't really do that. And without models that can properly simulate the lower cell, we can't really test theories. So on the other hand, one thing that the observations don't give us very robustly is an estimate of the total magnitude of the lower cell. And I've seen estimates in the literature ranging from 10 sverdrups to 50 sverdrups. Some of the observationalists might like to comment on that after the talk, but I think there is a bit of work to do there. I'd love to talk about models relating to the lower cell, but as I said, models don't really do a very good job of the lower cell. So instead, I'm going to jump straight to the complications. And if there's anything that the models tell us, they tell us that the lower cell that we can simulate in models, if you freshen or you warm the surface near Antarctica, then you'll reduce Antarctic bottom water formation. And that's not rocket science. I'd also ask the question is how it's sensitive to wind stress forcing, because wind stresses close to the Antarctic coast may change in the future or may have changed recently, and that may be important. In particular, some model simulations, we see that when we change the winds and we change the upper cell, that the lower cell reduces by the same amount. In other models, you don't get that. In other models, they're independent. So the coupling between the upper and the lower cell, I think, is an important and interesting question that hasn't really been addressed. We need to know more about buoyancy fluxes. There's some promising mechanisms to study buoyancy fluxes. For example, the sea ice thickness measurements of Tamura and his group in Hokkaido. Well, there's another couple of points here. I think the lower cell may be as important or more important to carbon than the upper cell, particularly on long time scales. But I don't know of any estimates of carbon uptake in these regions, and I'd love to be corrected on that. One of the things I want to work on is how we can better model all the processes involved in bottom water formation for the entrainment, the formation, the sea ice processes, and the abyssal processes. Okay, so my red light's flashing, so I'm going to stop there. I've got some conclusions up here, but I think I prefer to leave them there and leave some time for questions. Thank you.